Hello and welcome again to Digital ASIC Design. In the next few videos we're going to cover these four topics. What I like to call the wonderful world of silicon, that is why silicon is such an important technology and why ASIC design is such an important technology. Then we're going to get into the different types of ASICs and how does one choose which type to use for which application. And then after reviewing the ASIC design flow, we'll talk about trends in this industry that are strong drivers towards certain changes. These are the objectives and motivation for this particular module as a whole. The objectives are as listed as the top there, and they relate to the four topics I listed on the previous slide. But the reason for doing this is I'm putting ASIC design within a global perspective. Why this is an important and thriving industry, why this is an industry with high levels of growth. I'm also going to put this class in the context of the entire design flow, because we're not dealing with the entire chip design flow, just what's called the front end part of it, that is defining the logic. These are the references, including some online references. So in this sub-module, I'm going to talk about these two topics. Silicon as a complex engineered system, and within the context of Moore's Law. What does Moore's Law mean, and what are its implications for this industry? So here are two of the crowning technological achievements of the 20th century, though the graphics engine comes from this century. But you can consider these are two of the few big, huge engineered achievements. The moon program, as typified by the Saturn V rocket, and silicon, as typified by this graphics engine on the right. And I'll ask you the question on this page: which is more complex? How do you measure complexity? Let's try a number of parts in the system. The Saturn V rocket has 350,000 parts. The chip on the right has over 1 billion parts. Admittedly, there are more unique parts in the Saturn V rocket, but just in terms of component count or subcomponent count, the silicon chip is more complex than the Saturn V rocket, and even entirely the Saturn V system with the Apollo system, with the rocket and the Apollo module and LEM and so on. Let's try another metric. Let's try money spent. The total moon program from 1961 to 1973 consumed about $120 billion in today's money. Okay, that's a lot of money. The semiconductor industry generates over $300 billion a year in revenue. Given that a big fraction of that, say 10 or 15%, is invested back in the industry, in the fabs and design capabilities and so on, then the amount of money that's gone into getting to where we can make the chip on the right was more than the amount of money we spent putting 12 men on the moon. So you could actually argue that a silicon chip is the most complex engineered artifact ever designed by man. And it is your honor, your privilege, to join the ranks of those few engineers who get to design and deliver these chips. And of course, as you realize, the implications of both these systems have been huge on mankind. Talking specifically about silicon, the internet is enabled entirely and driven entirely by these complex silicon chips we can build. Mobile devices can only achieve their computation at such a low power level because of these silicon chips we can build in these advanced technologies. And they're just some examples of the things that have been enabled by the digital revolution, which has been enabled by the semiconductor industry, and very specifically by ability to design complex functions quickly using hardware description languages and logic synthesis. A driving law in the silicon industry is Moore's law. Gordon Moore, Intel, observed in the mid-60s that the number of components per integrated circuit, which was invented in the late 50s, the number of components, number of transistors per integrated circuit was increasing exponentially at time. And there's a plot from his paper on this on the right. In 1959 we had 1 transistor, then 2, then 4, then 8 in 1965. And to everyone's amazement, the industry and academia was able to solve problem after problem to keep us on this exponential curve until today and until well into the next decade. This has been an incredible achievement to keep an industry on an exponential growth curve over this period. There's no industry that has an exponential growth curve, particularly one that lasts so long. So let's see, if automobiles were on an exponential growth curve, where would it be today if you compare them with computer chips? We'd be able to drive at tens of thousands of miles an hour. We'd consume 1 million miles per gallon in power consumption. And we'd crash and burn every day while debugging the car. So this has been a unique achievement to have this exponential growth law. There's some corollaries of being able to put more functions onto a chip per year. Obviously, you can do more with each chip. The cost of each transistor goes down. And because the way we're doing this, by making the transistors smaller, the speed of each transistor goes up. So the reason for this, of course, is we've been able to constantly decrease the lithographic feature size as measured by the transistor gate length. Right now we're well into the 22 nanometer node, and we're expected to keep going till transistors are about 5 nanometers, possibly 1 generation after that. Same time, the wafer size has increased slowly, but this is still dramatic in terms of the number of chips per wafer, and we've been having to increase the number of metal interconnect layers in order to cope with interconnect delay, and we'll come back to that later. But the main thing is this dramatic reduction in time with the transistor gate length. Here's an example on the right. This is a quote-unquote 45 nanometer technology. This is a side profile of the transistor. In circle, we see the strained silicon. That's the channel of the transistor. Then we have a gate oxide above it to the gate electrode that's above that. And that's just illustrating what's going on. At the same time, the cost of making each wafer, even though the transistors are shrinking and the size of the wafer is slowly increasing, the cost of making each wafer stays roughly constant at somewhere between $1,000 and $2,000 per wafer while it's a leading edge wafer. And the yield, that is the number of parts that work, has continued on the same curves. When you introduce a new generation, the yield is low, and fairly quickly the yields are in the 90% range, even for relatively large chips. So in high volumes, the cost per chip has stayed, actually improved slightly due to increasing wafer size over time. Though you can argue, depending on the details of the costing, it's stayed roughly the same, maybe improved a little bit. However, unfortunately, and we'll talk about this at the end of this module, the cost to the first chip scales up dramatically with time. This is because the design complexity goes up as the number of transistors go up and the lithography size goes down. And the cost of making these masks with these tiny features on them goes up dramatically with each new generation as well. Talking about generations, I want to refer specifically here to the ITRS, the International Technology Roadmap for Semiconductors. This is a planning document generated by the industry on a bi-yearly basis. I'm actually involved in helping prepare this document. And what it's meant to do is to identify the barriers to staying on this Moore's law growth curve and identify what the possible solutions are, at least been identified by others. So it produces pages like this. These are tables, not necessarily being predictive or prescriptive, but showing the trends, and with a commentary discussing what problems have to be solved to actually enable this trend. So some interesting things on this page. I'm going to refer to the top slides here, the top lines here later on the next page. But down below this we have the functions per chip at introduction. And you can see today we're routinely building chips with 2 billion transistors. And within a few years we'll be over 15 billion transistors per chip. And this is because of Moore's law, because of the decreasing feature size. And the density goes up because the transistor sizes goes down, as you can see by the bottom here. This slide, the figure on the left, shows the specific trend for memories. For SRAM, the top lines, for DRAM, the middle line, and for flash, the bottom line. You notice the scale on the left, which is basically density, is logarithmic. Straight lines on a logarithmic graph are exponential curves. So this illustrates the exponential nature with historic data and future projected data. You'll notice actually that flash has been a little bit better than exponential for the last decade, and this is because of some specific innovations that came from the flash industry. But this just illustrates this point. On the right, I've used this figure to introduce a specific concept. Going back a page, the half pitch, the top 3 lines in this graph, in this table. The half pitch is what is referred to as the quote-unquote ITRS node. That is, when we say a technology is a 16 nanometer technology, is referred to or 32 nanometer technology is referring to this table, one of these top 3 lines, depending on what type of process it is, because a flash process is different than a DRAM process, which is different from a logic process as used in an ASIC. What this quote-unquote ITRS technology node specifically means is the half pitch, that is half the metal pitch in the densest metal of the chip. This is the metal layer closest to the transistors. It is actually only indirectly related to the transistor size. So obviously there is a strong correlation, because this is illustrating the prowess of the semiconductor process technology in the lithography. So here we have again another table. This is the cost table. Again, the half pitch is at the top there. And you'll notice lines 4 and 5 refer to the printed gate length and the physical gate length. As you can see, the printed gate length is very closely related to the line above it, the half pitch. The physical gate length is shorter due to reasons we don't have time to go into. But as you can see, the physical gate length, which actually determines the performance of the transistor, isn't scaling quite as fast as the printed gate length. What's interesting in the bottom parts of this table is the cost per transistor. And notice what it's measured in, microcents. In fact, on the right-hand side, we're saying in 2016, a high-performance MPU, the volume cost per transistor will be 540 nanocents. This is a true nanotechnology where it only costs nanocents per function. This, of course, in contrast with where this all started with Moore's law a few pages ago, that the cost per transistor was many dollars. Now, of course, when you can produce each transistor at lower cost, you can put more of them on the chip and produce the chip at the same cost. So in mobile, you typically make a $10 chip at the core of a mobile unit. Each generation, that $10 chip can do exponentially more because it has exponentially more chips on there, transistors on there at the same chip cost, and those transistors are faster and consume less power. Thus, with each generation, the capability of that core mobile product is exponentially improved, is doubled or more over that of the previous generation. And guess what? Someone has to design that new chip each generation. In mobile, the generations come fairly quickly, just every few years. In graphics, it's a little slower, about every 5 years. But nonetheless, there's constant redesign of these chips as we can fit more transistors and more functions onto the chip at the same cost and at the same power consumption. This, of course, drives high employment in this industry because we need lots of designers to do this constant redesign and redefinition of these ever-increasing complexity chips. And that actually is one of the beauties of this industry. Because of this constant change in the underlying technology and its capabilities, we constantly have to redesign it. Compare this with other engineering functions. How often does a bridge get redesigned? Not very often. In fact, never, basically. At least in the United States, as demonstrated by some recent failures. How often does a car get redesigned? It doesn't change dramatically. Yes, it changes, it evolves. In fact, it's electronics that's driving most of that evolution right now. But it doesn't change fast, and thus the number of car designers is relatively small. But the number of chip designers is relatively large. And of course, one of the reasons you're taking this course is to join those ranks. So that brings us to the end of this particular submodule. I'll remind you that the silicon chips represent a crowning technological achievement of the 20th century that's continuing in the 21st century. And part of the reason for this is transistor density has increased exponentially with time since 1959. And over 50 years later, we're still on a transistor density exponential growth curve. This is referred to as Moore's Law. And Moore's Law has had profound implications on the growth of digital processing capability, enabling all the functions of the digital revolution, which will change again within the next decade as we continue on this Moore's Law growth path. Next, what I ask you to do is take the submodule quiz. I remind you that the quizzes between the submodules, though I do keep the score does not count as part of your grade if you're taking this as a graded class. And then go on to the next submodule, please. Thank you very much.